Hello everyone. Today we are going to explore the work, a deep generative model for graph layout. This research introduces an innovative approach to generate diverse graph layouts using a deep generative model. In this presentation, I will break down the problem that this paper has addressed, explain the proposed solution, and show the results and the impact of this work. Let's begin with the graph visualization and the layouts. Graph visualization allows us to explore the complex relationships in systems such as social networks, protein interactions, and data communication. And the most popular and intuitive way to visualize a graph is a load link diagram, where the loads are drawn as points and the links are drawn as lines. Here are three examples of load link diagrams. These load link figures correspond to the three complex systems mentioned before. Compared to the raw graph data, we can see that these figures can clearly reflect the interdependencies between these loads. The layout or arrangement of loads and edges is essential for uncovering the hidden patterns in the graphs, such as communities and clusters. Good layouts make structures easy to find these hidden patterns, while poor layouts can obscure meaningful information. For example, in a social network, a well-designed layout can reveal tightly collected groups of users. In fact, graph layout is a subset of graph visualization. The layout specifically deals with positional nodes and edges, while visualization refers to the entire process of graph representation, including color, labels, and other visual cues. In this paper, we focus on visualizing graphs by suitable graph layout. The motivation for this research comes from the need to effectively visualize complex systems through graphs. Graph layouts are crucial for highlighting relationships, but different layouts focus on different features. In this case, there's no single best layout. We just need to choose the graph layout that is the most appropriate for our research. A good layout depends on what we want to highlight, the type of graph, and the user preferences. Finding a good layout of a graph is a challenging task. The heuristics to find a good layout are nearly impossible to define. It requires to consider many different graphs, characteristics to be highlighted, and user preferences. Therefore, there is no existing method to automatically find a good layout. Traditionally, generating a good layout involves continuous trial and error with different algorithms and parameter settings. This process often requires a significant amount of users' time, as it results in a complex exploration of a large number of layouts. To help users to produce a layout that best suits their requirements, this paper introduces a deep generative model that systematically visualizes a graph in diverse layouts. This model significantly simplifies graph layout. In fact, this model can enable users to intuitively explore layout possibilities in a structured latent space and avoid manually adjusting the parameters of the layout method. One challenge in applying machine learning to graph layouts is deciding what features to use. The raw load positions are unreliable due to the randomness in many layout methods, such as force-directed layouts. The authors decide to use the pairwise Euclidean distance between nodes as layout feature. This captures the spatial proximity between nodes, which is essential for determining the visual structure and the relationships in the graph. To compare layouts across different scales, the pairwise distance matrix is normalized by dividing each entry by the mean of all distances in the layout. This ensures that the layouts of different sizes or scales can be compared on a consistent basis. Then let's talk about structure equivalence. It is an important issue that this paper takes into account. The two loads are structurally equivalent if they share the same neighbors, and the structurally equivalent nodes should be placed in a similar location of the layout. However, many layout methods, such as force-directed methods, prevent nodes from overlapping by applying repulsive forces, which can cause structurally equivalent nodes to appear far apart in the same layout. This variability makes it difficult to compare layouts directly based on node positions. For instance, the right figure shows two different layout results of the same graph by using the same layout method with the same parameters. The blue nodes are the same set of structurally equivalent nodes. We can see that the blue nodes are 624, 351. However, the arrangements of the blue nodes between the two layouts are quite different. In the top layout, the nodes 624 are closer to 78 than 651. In contrast, in the bottom layout, the nodes 534 are closer to 78 than 261. This presents a challenge because a permutation invariant measure of similarity is needed for the same set of structurally equivalent nodes, such that we can obtain a visually correct similarity measure. To address this challenge, did the authors use the GW distance? The formulation of the calculation of GW distance is shown in this slide. This metric compares two layouts of structurally equivalent nodes by finding the optimal alignment between the sets of structurally equivalent nodes in different layouts. In fact, the GW distance helps measure the dissimilarity between two metric spaces. Here, the metric spaces means the layouts of the graph, while being invariant to the permutations of the structurally equivalent nodes. The GW distance produces a permutation matrix that reorders the positions of structurally equivalent nodes in order to align them correctly between different layouts. This allows for a visually accurate comparison of structurally equivalent nodes, regardless of their specific layout positions. However, to save on computation cost, the proposed model does not backpropagate through the GW distance. Instead, it uses the permutation matrix from the GW computation to adjust the layout and then calculates the reconstruction loss between the adjusted input layout and the generated layout. In this paper, the deep generative model uses an encoder-decoder architecture. It follows the framework of variational autoencoders to learn from a collection of example graph layouts. Here is an overview of the architecture. In this figure, it shows the architecture of the proposed model. On the left, we have the encoder. The encoder takes in graph layouts and maps them into a point in no-dimensional latent space. On the right, the decoder takes a point from the latent space and generates a corresponding layout. What's innovative here is the creation of a two-dimensional latent space. In this latent space, similar layouts are close together. Users can explore this space to find layouts without needing to understand or adjust the underlying algorithm parameters. This architecture allows us to navigate through various graph layouts simply by moving through the latent space. Then let's discuss the key components of this architecture concretely. The encoder is responsible for transforming input graph layouts into a lower dimensional latent representation. It has 4 operations, as the slide shows. In the stage of feature extraction, the encoder takes a graph layout where the primary features are pairwise Euclidean distance between node positions. These features help capture special relationships between nodes without worrying about absolute positions or orientations of the graph. For graph structure awareness, the encoder uses graph neural networks to capture the structural properties of the graph. Graph neural networks work by iteratively aggregating information from neighboring nodes to compute node embeddings. The final node representation is influenced by the graph's structure and the layout. After processing the graph, the encoder outputs a low-dimensional latent space representation of the graph layout. Specifically, the latent space is two-dimensional, allowing users to easily navigate and implement the layout. This is key to models design because the two-dimensional space serves as a user interface, enabling interactive exploration of graph layouts. After aggregating the node-level representations, the encoder combines these features into a single graph-level representation. This helps the model capture both node-specific and graph-wide layout features. As for the decoder is going to reconstruct the graph layouts from the latent space representation. Before the features are fed into the decoder, they need to be pre-processed by the fusion layer. The fusion layer receives both the graph level latent representation and the node level identity features which are one-hot encoded. These features are combined in the fusion layer to preserve both the graph's global structure and the identity of individual nodes. After that, using the fused features, The decoder reconstructs the layout by predicting the position of each node in the graph. The feature of the reconstructed layout is computed for measuring the reconstruction loss. After training, users can generate diverse layouts by feeding different layout latent representations to the decoder. Then let's talk about the training loss. Following the framework of variational autoencoders, the parameters of the neural network used in the generative model are learned by minimizing the reconstruction loss and the variational loss. The reconstruction loss measures the difference between the input layout and the layout generated by the model using the layout features. The goal is to accurately reconstruct the orange layout from its latent representation. The variational loss is calculated using the sliced Gaussian distance, and it regularizes the latent space by encouraging the latent representations of layouts to follow a predefined distribution. This helps ensure smooth transitions in the latent space, enabling the generation of diverse layouts. For the model that learns to generate graph layouts, it needs a large and diverse dataset. The authors create this dataset by using multiple layout methods and random search to generate different layouts, as shown in this table. The authors apply 4 layout algorithms, each with different parameter settings, to generate training dataset. The authors use random search to randomly select parameter values from predefined ranges for each layout method. From this table, we can see that these 4 layout methods have different parameters, such as link distance, force model, and force strings. And each parameter is determined in a range that have been defined in this table. This approach ensures to produce more diverse layouts with a wide range of characteristics, from aesthetically pleasing to cluttered or hairborne layouts. This diversity allows the model to learn general patterns and the relationships between graph structures and layouts, rather than memorizing specific examples. This ensures that the proposed model could generalize well to new graphs, since generating all layouts can be time-consuming. The model is trained incrementally using stochastic optimization. This allows the training to start before the full dataset is available, and the layouts can be generated continuously throughout the training process. And in this way, the model can be used by the users very soon. To obtain the training dataset, the authors use 9 real-world graphs that are shown in this table. We can see that these graphs have different characteristics. Each graph has a different number of vertices and edges, as well as a varying ratio of the number of edges and vertices. This ensures that the training dataset contains graphs of various sizes, such that the trained model can deal with graphs with arbitrary sizes. The authors use the 4 layout method mentioned earlier to produce 20,000 layouts for each graph, and these layouts are regarded as the training dataset to train the generative model. The authors evaluate the model both quantitatively and qualitatively. Quantitative results show that the model performs well at reconstructing unseen layouts with low reconstruction error, especially when using graph neural network layers and GW distance. This indicates that it has learned meaningful patterns from the training data. Qualitative results show that the model's ability to generate diverse, smooth, and intuitive graph layouts that are visually coherent and spatially stable, which allows for interactive exploration of the layout space. This demonstrates that the proposed model achieves significant improvement over traditional methods that can produce inconsistent results. Then let's discuss the quantitative evaluation. Quantitative evaluation of the model focuses on the reconstruction loss on a test set of unseen graph layouts. The reconstruction layout loss measures how accurately the model can recreate layouts from their latent space representation. Lower reconstruction loss indicates better generalization. The authors performed 5-fold cross validations to compare the performance of the 8 model designs. To reduce the effects of the photo assignments, the experiment is repeated for 10 times, and the mean losses are reported in this figure. Overall, the models with graph isomorphism, neural network, MLP, and GW distance show the lowest loss of all the graphs. Specifically, the models with graph neural networks layers, particularly the graph convolutional neural networks perform better at capturing graph structure and reducing reconstruction loss compared to the simple models, such as the MLP-based models. The inclusion of the GW distance, particularly for graphs with structurally equivalent loads, leads to better reconstruction accuracy by handling permutation invariance in structurally equivalent loads, further improving the quantitative results. As for the qualitative evaluation, the qualitative evaluation provides insights into how well the models learns the abstract concepts of graph layouts and how effectively users can explore the layout space. This figure shows the qualitative results of a spatial graph using the 4 different models. These 4 models are MLP plus GW distance, graph isomorphism network plus MLP, and the combination of graph isomorphism network, MLP, and GW distance, respectively. These results indicate that the model is able to generate layouts that are loaded in the training set, but still adhere to the abstract principles of good graph layout design. For example, in the last row of the figure, the input layouts are hairballs. In contrast, the layouts that are reconstructed by using the proposed model are more organized. Yes, we can see that from this figure. And this observation demonstrates that the model learns to generalize concepts rather than memorizing specific examples. To demonstrate the proposed models with more graphs, this figure shows the qualitative results of 5 different graphs using the graph isomorphism network MLP model for the football graph and the graph isomorphism network MLP plus GW distance models for the other graphs. The first 3 rows show that the proposed models are capable of many different styles of the layouts, while for the bottom 2 rows, they show that the model's behavior on hairboard-like input layouts. We can see that the reconstructed layouts are more organized. For example, the fourth layout of DWT 419 is twisted. However, the reconstructed layout is not twisted, but located near the center, just like the other organized layouts. A common way to qualitatively evaluate a generative model is to show the interpolations between the different variables. If the transitions between the generated samples based on the interpolation in the latent space are smooth, we can conclude that the generative model has a generalization capability of producing new samples that are not seen in the training set. This figure shows the results of 2 specific graphs. As we can see, the transitions between the generated samples are smooth. This indicates that the model captures continuous variations in layout styles, which enables users to explore gradual changes in graph representations. The orders build what you see is what you get inference for users to intuitively produce a layout that satisfies their requirements. Users can browse the layout space by simply interacting with the latent space, making it easier for non-experts to find the layouts that suit their specific visualization requirements. And there is no need to have expert knowledge about layout algorithms. This figure shows an example of the generative graph layout. In this interface, we can choose 3 parameters: the graph, neural networks, that is the model, and we can see that whether the model plus GW distance or not, and the layout matrix. For example, in this figure, we can see that the layout matrix is a crossless list. The model allows users to explore different graph layouts interactively. By navigating the 2-dimensional latent space, users can generate and visualize diverse graph layouts without manually adjusting complex parameters. The users just need to place the mouse at a certain point in the latent space, just as shown in the right figure, and the corresponding layout will appear on the right. This provides a more intuitive approach to layout generation compared to traditional methods. At last, let's talk about the further challenges and future work. While this model represents a major advancement, there are still challenges. The model might face difficulties with very large or complex graphs, and the training requires significant computational resources. Therefore, the model needs continuous improvement to deal with these issues. In the future, the authors proposed three research directions. The first one is to extend the model to handle three-dimensional layouts. The second one is to integrate users' feedback into the process, such that the model can produce the graph layouts that can better satisfy the requirements of users more easily. The third one is to tackle dynamic graphs, which are very important. To summarize, this paper makes significant contributions to graph visualization by introducing a deep generative model for graph layout generation. The encoder-decoder architecture and two-dimensional latent space allow for intuitive and efficient layout generation. By exploring the latent space in the interactive interface, the user just shown in that website, the users can obtain the good layouts, whether they want to emphasize global patterns, cluster relationships, or local structures. Compared to traditional layout methods, this model has several advantages. First, it's much faster at generating layouts since users don't need to manually adjust parameters. It's also easier for long exports to use as the latent space provides an intuitive interface and for exploring layouts. Finally, the visual stability offered by this model ensures that the small changes in layout are gradual and easy to interpret. This work has broad application from social network analysis to biological data visualization. Okay, that's all for today's presentation. Thank you.